So to start this project, I want to give you a general idea of what is happening with the structure that we see here. It's positioned at the center of the canvas. It appears to be multiple versions of essentially the same shape, but it's offset in its position and it's offset in its scale, or the shape that's being described at that moment in time. So we can see some of them are inflating and then deflating, expanding and contracting, and it seems to be doing it in a cycle. So we know that we're using maybe a loop is going to be there, maybe a recursive algorithm inside that loop, and then all of this is going to be translated or positioned in the center of the canvas. So we have a general idea of what we're doing. I'm going to use the available window width and window height for this sketch, and in the global space we need to declare two variables. We're dealing with a recursion, and that recursion is made up of segments of decreasing length, and the angle between the segments can be rotated slightly, and it's going to give you this blade shape. I'm going to call it a blade. So that length needs a starting size that will be its maximum length, because as it's decreasing it's never going to be larger than that. And then we need a minimum size, some place to stop the recursion so that it doesn't run off into infinity. So we're going to declare those variables in the global space so that we can use those in draw and in the recursion without them changing. So they're going to kind of remain a constant inside the recursion, and then if we want to, we can change them inside draw a little bit, and then that will carry out into the global space, and then the recursive algorithms can use that variable, and it's not going to change inside the recursion. Does that make any sense? I've tried to set up a recursion with these variables inside of it. It just doesn't work right for some reason. So I'm just going to make them global variables. Kind of a long way around that. So I'm going to call those max len and min len for maximum length and minimum length. Let's assign these values in setup just so we'll have some initial state. And we'll use them as constants for now, but later on we might want to alter the length. As you can see in the output here on the right, the length of the segments are being increased and decreased cyclically. So at some point in the sketch we're going to want to alter these values. But for now I'm going to leave them static so we can see what's happening, and then we'll change them and you'll be able to see how that change directly affects these procedures. So for our initial value for the maximum length, we want it to be a proportion of the height. We want it to be a small portion because the starting length, this maximum length that we're giving to the recursion, it's just one segment, and added to it will be another segment that's slightly shorter. So if we start out with a large maximum length, our recursion is going to be built off of the canvas. So we're going to keep this small so that everything is inside our border. So we'll take 1/5 of the height, and for our minimum length we'll just take 1/5 of our maximum length, so everything is always in proportion. So we have those two values. Now let's build our recursion first. I've done this video, recorded it a couple times, and I've always done the body of draw first and then done the recursion. And I think that that might be a little bit confusing. So I'm going to start with the recursion and get that out of the way, and then we can build draw. Okay, I'm going to call the function Blademaker, and it's just a method, so we can call it inside of itself, and we don't have to instantiate it or anything like that. So Blademaker is going to want to receive two variables. It's going to want to receive a value for the length that we're going to be operating with inside the recursion, and it's going to want an angle to move that segment around the origin. So let's give it a value for the length. Let's just call that len, and for the angle let's call that theta. So inside the body of this function, let's isolate any changes to the graphic state with push and pop. The reason why we do this is because when we call the recursion inside of itself, we want to make sure that all of the rotations and translations are accumulated throughout every level of the recursion. And if we didn't isolate that call inside push and pop, it would lose its locations of where these segments are supposed to connect to one another. So that's why we isolate it. And then we want to translate to the origin, so that when we rotate the segment, we're going to draw it from that origin, we're going to rotate it around it. It's going to rotate from the beginning of the segment and not the center or the end or something like that. Once we've translated, we want to rotate that segment at its base. We're going to do that by the angle that's been sent into the parameter of the recursion. Next, we want to, well, you don't have to, but this is a step that you can do if you like. You can see in the output there that the base of the recursion has a thin line, and then it gets thicker for each segment it goes out toward the end. So essentially what we've done here is we've interpolated the length of a segment to a width of the stroke. To do that, we're going to use map. I'll assign stroke weight to the return of map value. We're going to use length for our parameter, and we already have the maximum value here and the minimum value, our range values, and those are minimum and maximum length that we have in our global space. Now the order of these two things here are kind of arbitrary. It doesn't have to be the lowest number first. What's important is whatever order those are in, your interpolated range corresponds to that. So that's kind of a tip. You can switch those around if you want. It's not important, just so long as you remain consistent. We have our stroke weight value. We can set that. We can set our stroke to contrast our background. Later on, you might want to set a color value and interpolate it to the length or the width or whatever, so you can get different color bands for different lengths of segments. Once we have our stroke and our stroke weight, we can draw our line from the origin, 0, 0, to the length of that segment. Now we can do this along the X or the Y, it doesn't matter. Typically what the convention is when you're making a recursive tree, you're drawing it from the ground upward. So your segment is going to go into the negative Y quadrant. I'm just going to maintain that convention just out of, I don't want to defy convention and then revert back to it and then I have some error somewhere. So I'm just going to stick with what I know. But again, you can use any of these positions. You can use the negative X or the positive X, negative Y, positive Y, just as long as you're consistent whenever you translate. After you make your line, what we want to do is we want to change the origin to the end of that segment. So if you use a negative X, if you're drawing from the origin to the left, then you want to translate from the origin to the left. Else, nothing's going to line up right. So once we've drawn our line, we've translated to the end of that segment, we can do a test and see if we have a segment that's long enough to perform this recursion again. And if we do, we're going to just call the Blademaker function again, send in the parameters again, but we're going to alter those slightly. If the segment isn't long enough to do the recursion again, then the recursion is just going to end, and that segment, that blade, will have been built. So we'll ask the question, is the length of this segment greater than its minimum length? And if it is, let's make another segment. Now if we don't alter the length, this is going to carry on for infinity. So we have to alter the length in such a way that it will eventually answer no to this test. So we're testing against the minimum length. Let's reduce the length by a little bit each time. So eventually it'll get short enough that this condition will be no and the recursive algorithm will be ended. To do that, we're going to take the length value that was sent into the recursion. We're going to multiply it times a fraction. And let's make it a small fraction to begin with. We can adjust this later, but it's always better to start small because you're making fewer segments and you're not going to tie up the processor as much that way. Now theta isn't being tested, so it can stay the same or it can be changed in a variety of ways. If it stays the same, you're just going to make a stick. So we want to change it a little bit. We want the angle to either increase or decrease by a small amount each time through the recursion. We can do that by multiplying it times 1 point a number. I'll say 1.1. So basically, each time through the recursion, I'm taking whatever the value of theta is, and I'm adding 10% to it. So that angle is increasing. So as we make each segment and the angle is increasing, that blade is going to curl. It's going to fold up and curl onto itself in one way or the other. If it's a positive value, it's going to go to the right or clockwise. If it's a negative value, it's going to go to the left. Once we have our recursion built, that looks good. I think that will work. Now let's start with how we're going to make this recursion show up the way we want it in the output. So we'll make a contrasting background, full opacity, so that we completely clear the output each frame. We want a clear view of what's happening. Once everything is in position and it looks nice, then we could adjust the opacities of the stroke and the background to get the blurring and the trails and all the nice effects that are going to take this to the next level. Okay, so our subject of this art is in the center of the canvas. So let's translate to the center, and then we can grow each blade from that center point as if it were the ground. Our Blademaker function is receiving two variables. It's receiving a length, which we have that length, that's the maximum length. We can send that into the recursion and it can operate with that. But it also needs an angle. So let's make one blade and put some values in there and see what happens. Okay, I'm going to use a fraction of pi for our angle that we're sending into the recursion, and it's going to draw one version of that blade, and it should be rotating, or no, it isn't. I left that part out. Okay, let me put this in here. As a matter of fact, no, let's not do that yet. Let's see what it looks like just the way that it is. All right, so if I change the starting angle, you can see what happens there. If I make it a negative value, the other way. Okay, simple enough. So it's just staying in the middle of the screen. It's not doing anything, right? So let's put some movement into this. Let's put a rotation here. So we're going to rotate the canvas around the origin by a persistent value. So we can use frame count because it is always incrementing by an integer, and that's pretty easy enough to figure. Inside rotate, though, I'm dealing with radians, and I don't want to use a one integer increment inside there because it's going to be moving around way too fast that way. So if I just take a fraction of frame count inside the parameter of rotate, it's going to rotate the canvas slowly enough that we can see what's happening. So that's 1/100th. Let's try 1/10 of frame count, and I'll show you how fast that goes. And if I just use the full frame count, it's in, you really can't see anything that's happening. So you want to use a fraction of frame count. We're going to use 1/100th, and we're going to be consistent about that. So I'll explain that a little bit later, but we're going to use this value a lot. I could probably put it in its own variable, and I may want to do that. I'm going to do that. We're just going to do that for now since we're using the same result throughout our program. So I just have one instance of the blade there, and it's moving around, and it's not changing in its angle because I'm giving it a static value to begin with. So this is what we want to work on next. I'm going to make a variable called angle. An angle can be a small number between -1 and 1, and we can use cosine or sine to give us a value between -1 and 1. If we just give it a parameter like the FC variable, and it will keep doing this oscillation back and forth, which is ideal for this kind of art. So let's make that variable. If we just stay consistent and put FC in there, it's going to oscillate back and forth at the same rate that it's rotating around the origin. So let's look at this and see what that does. So just on its own, it's not, it's not particularly interesting. It is kind of cool what it's doing. So we can duplicate this branch, and instead of having a positive angle, just like we did before, we can put a negative angle here, get some symmetry. Now that's a little bit more interesting. Now this is the idea. We're going to start stacking these instances of this blade around the center and offset them in a uniform way so that we can get these patterns to emerge. Let's get rid of this here. Let's just blank it out for now. And we want to make multiple instances of this blade, and we want them to be offset as they go around the circle. So basically we need a variable that will describe the circumference of a circle. It'll take steps of that circumference until it describes a circle, and however many steps it takes, that's the number of instances of this blade that you'll have moving around the center. So to demonstrate that, I'm going to create a loop right after we rotate the canvas the first time. So around this push and pop, where we've encapsulated any changes to the graphic state within push and pop, and if we put that inside of our loop, it'll just continue that kind of order. Okay, so I've created a loop, and inside the loop it's making our blade and it's rotating around the origin. We're moving through this circle loop by a fraction of tau. So here it's just 1/10 of tau, and that's 2 pi, or a full circle. You can use radians if you want. If you want to work in degrees, you can. Just stay consistent, whatever works best for you. I like working in pi. So for this setting, it's going to make 10 instances of this blade each time it goes, it finishes the loop. So let's see what that looks like. And I don't see 10 of them, and the reason why we don't is because they're all moving around the origin at the same rate. So let's offset it. We're going to take this R variable, which is kind of a change over time, and we're going to apply it to the rotation. So each time we rotate a blade, it's going to get rotated a uniform amount that's applied concurrently, and then we're going to rotate by R, which is changing each time through this loop. So it's applying a consecutive change to them at the same time. So let's see what that looks like. And let's add some symmetry. And now we're starting to get into that snowflake appearance. So that's all well and good, but there's lots of things that we can change that will make this even more interesting. For instance, this technique of applying the change over time, we can apply it to the angle as well. So now we've offset the angle that we're bending these by to start with, and we're adding that to the change in frame count. And you can see how it creates this kind of cyclic pattern where there's a periodicity to it. So what are some other things that we can do? Well, we can adjust the maximum length by changing that variable inside the loop. Let's do that. Now this is what it looked like initially. So we know that we have at least this fraction of height to work with. So if we just make a variable oscillate back and forth and then multiply it times this small fraction, and then take that answer and multiply it times height, it's going to give us a range of starting lengths. So let's use cosine for this again, and we're going to put in the R plus frame count so it will change over time. And we want to take that answer and multiply it times a fraction. The reason why is because cosine is returning -1 to 1, and if we multiply height times 1, our starting segment is going to be the full height value, and we want it to be a fraction of the full height value. So we're going to multiply the return from cosine by this fraction, so it'll give us that small segment range. Now I just said that it's going to return -1 or 1, so a value between -1 and 1. We can't have negative values for our starting length because it messes with our recursion, so we have to make sure that this return is always positive. We can do that by using the ABS method. It'll return the absolute value of this return. So once we've done that, we need to also adjust the minimum length. That's easily enough done. Will stay in proportion to the maximum length. No matter what it is, the minimum length will always be 1/5. So let's see what this looks like. So now each branch is growing and shrinking at an offset rate, and when all of those instances are accumulated on the screen, it creates this really cool pattern. So let's add more instances. Let me take off this right here so we can see something that's really interesting. So that's a cardioid shape. Let me take this up a little bit so we can see more of what's happening. Down here in our branch recursion, let's flip this around. I'll show you what that does. Now it's going to be thin to begin with and thicker on the outside. And if we add some symmetry, we get a really cool shape. Now we've used cosine for our angle and cosine for our change in length. What if we use cosine for our change in angle against our sine for our change in the length? Let's see what that does. So it's going to create a different type of pattern. Let's take away one of those branches, so we'll break the symmetry there and show you this interesting shape here. Alright, so let's set this back to very few instances. So we're just going to have a few there. Let's have 5. So down here, our recursion, we just have a one branch recursion, but if we copy the middle of that and then paste it below, now we're making 2 branches, and we're making identical branches, so we want to flip it so we get the reflection. We can do that just by rotating the opposite way. And we've declared this already, so let's just reassign it. We don't have to declare it again. And let's see what this does. So now it's creating the branching and that really cool effect. So it's costing more in processing because we have far more segments being represented here than we did with the single branch recursion. And if I show the symmetry, it's going to take even longer. As you can flip things around, you can adjust the rotation in another way. So now it's rotating in the opposite direction. It almost looks like it's standing still. So this has to do with the intervals and the periodicity of how things are being rotated and how the angles are changing. Right now all of those are in parity because we're using the same variable up here, but we could choose to alter this, so we could do like frame count 0.5. So we're going to change them really fast. And that's going nuts. Let's take more pieces, see what that does. So if you were to like blur this, we'll lower the opacity of draw, and we'll go in here and lower the opacity of the stroke. And it might create some accumulative effect, some output that will grow over time that looks interesting. So you can play around with this in lots of different ways. So before I leave this video, I wanted to open up some So before I go, I wanted to show you how far you can take this. Here I've altered the recursion in such a way that now it has a branch from within itself, within the branching part. So it's a double branching recursion, and the second branch can come from anywhere along the length of the first branch. It's not fixed to the origin location. Now it can be put anywhere. Well, if you try to do that randomly in a recursion, these branches are going to be all over the place each cycle because that random number is changing. But you could use noise and a fixed changing variable that would walk through the same random numbers every time you go through the recursion. So every level of the recursion would end up with the same random numbers each time. So you get something that looks random, but it's reproducible. And it's not only reproducible, it's alterable. So in this one you can see it has the branching is altered slightly because I've changed one of the numbers here. I think it's down here in the recursion. Yes, it's diminishing by 7 here, and it's diminishing by 0.5 here. So let me load another one that will show you what I just talked about a second ago. Since I did talk about it, you might want to see it. Is it this one? So here's the one where it has the random looking branches, and I used noise and a fixed variable in order to get the same random numbers each time. So that's how I can get it to look random and be able to reproduce that randomness. You can alter this. I think I'm taking 2 of these per circle. Let's take 5 of them per circle, and you can see it kind of slows things down, but you get a richer variation of pattern. Let's just do 1 blade inside the loop, so we're breaking symmetry a little bit. But if we add more instances, also you can see that it's not rotating like it was before. I think I put some noise in there. Oh yeah, instead of oscillating the length of our segments, I'm using noise to change the length of the segments. And up here I think I'm rotating at the same rate, and I tried using noise to rotate the canvas by, but it just wasn't very interesting because most of the time it was just kind of staying there. So I thought, well, maybe I'll just add it to it and it will accumulate, and that would be okay. So I thought about adding it, and then sometimes it can really get going crazy in one direction or another as this value accumulates. So there's a number of strategies that you can use to manipulate any of the variables inside this loop, inside draw, and even inside the recursive function to get a lot of variety in the output. So I encourage you to play around with this, enjoy it, break it. Hopefully it won't break you. You'll find something that is really interesting and you'll be able to expand on it and make it your own. Thanks for watching. I hope you got something out of this. If you did, leave me a comment. If you want to see more videos like this, I don't upload a whole lot, but when I do, you might want to be notified. Hit the bell. Subscribe if you like content like this. This lets me know that there are people out there that may be interested, and it encourages me to post these in the future. So as always, thanks for watching, and until next time, take care.